This is the first time broadcasting. So I got some questions, and then you send me these questions through the Viber, and then I print them out on a piece of page, and then now, okay, the all right. This question is about a current-carrying conductor. So arranged so that electrons flow in one segment from south to north. Um, if the compass is held over this segment of the wire, in what directions the needle deflected? This is the first question I will explain. And first we should draw the directions, which is the north, and then is south, east, and west. Without drawing the directions, do not start answering the question. And we are going to locate a wire, which is from in the east. Question says that it is the south-north direction. So I'm going to locate a wire in the south-north direction. This is the wire, and the electrons flow in one segment of in this wire from south to north. So the electric current direction will be from south to north. But we know that electron motion, electric current directions are opposite. And after that, we are going to apply the right-hand rule. Remember, right-hand rule, thumb points in the direction of the electric current. So you are going to find the direction of the magnetic field just over the wire. So thumb is showing to the south. So the curved forefinger will point, and the forefinger is pointing to the west direction. So then compass, when you put the compass over this segment, over means just above, this compass must point to the west direction. So the answer of wire, not near, not below, just above, because over means above the wire. It's going to be west. Answer is west. Next question, question number, this is a sample question, a sample 5 bits about the it says that a long straight wire carries a current of intensity 6 ampere, where a part of is calculate the magnitude and the direction of the magnetic field at the center of the loop. The question is asking about this. So we will first do a wire, and then so in this case, this system will have two components. One component is the straight wire, so this is going to be the straight wire part, and second component is going to be the loop, so a single loop. And of course, both the straight wire and the loop will carry the same amount of the current, which is equal to 4 meters. So questions asking, calculate the magnitude and direction of the magnetic field at the center of the loop. So just here, calculate, find the direction of the magnetic field and also magnitude of the magnetic field at this point. So because there are two components, we have to find the magnetic field of the straight wire at the center of the loop first, and then after that we should find the magnetic field of the loop at the center. So we are going to have two magnetic fields. For straight wire, we start with the straight wire. So a straight wire must produce a magnetic field at this point, let's say O. So then I'm going to use the first right-hand rule to find the direction of the magnetic field because of the straight wire. So electric current direction is the thumb. Curled forefinger is into the page on the right side of the wire. So because the point O is on the right side of the wire, so your forefinger must stay on the right side, which is into the page. So let's say this is the first component, this is the second component. Yeah, the first component is the straight wire, second component is the loop. So B1, which is the magnetic field because of the straight wire, must be into the page, which is cross. So I will calculate B1. B1, remember, the magnetic field of a straight wire can be calculated by equation mu I over 2 pi d. It was the equation for finding the magnetic field of a current straight wire. Let's find this first. It is equal to mu, 4 pi times 10 to the power of -7 multiplied by 3.0, d is the radius of the loop, of course. So that's why we are going to write that distance as a radius, which is 0.04 meters. So then if we calculate the magnitude by using a calculator, the answer is going to be 3 times 10 to the power of negative 5 Tesla. And the direction of the magnetic field must be into the page at this location. And this is the straight wire produce a magnetic field, which is equal to 3 times 10 to the power negative 5 Tesla at this point, or which is the center of the circular loop. Second one is the loop itself. Loop itself also has a magnetic field at this point, so we should find. First, let's apply the loop or solenoid. We are going to apply the right hand rule like this. Forefinger will show the direction of the magnetic electric current, and thumb must point direction of the magnetic field at the center, which is out of the page. So my thumb is pointing out of the page for that reason. So B2 here must be out of the page, which is dot. And I'm going to calculate this B2 because which is the magnetic field because of the loop. Mu over mu multiplied by I multiplied by N and C for finding the magnitude of the magnetic field. So then mu 4 pi times 10 to the power of negative 7 multiplied by I, which is equal to 6 ampere, divided by 2R2 multiplied by 0.04, which is equal to almost if we use the calculator, 9.4 times 10 to the power of negative 5 Tesla, and which is the output. And we will find the resultant magnetic field. Because magnetic field is a vector quantity, we should apply vector addition method. If two vectors are in opposite directions, so we have to subtract them, subtract the smaller one from the greater one. So then the resultant magnetic field, must be, so B is equal to, which one is greater of V2? B2 minus, which one is smaller? B1. B2 minus B1. 5, which is into the page. Of course, the magnetic field must be in the same direction of the greater magnetic field, which is equal to almost 6.4 times 10 to the power negative 5 out of the page. So this is the answer of this question. The magnetic field at the center of the loop must be 6.4 times 10 to the power negative 5 Tesla, and it must be in the direction of the greater component of the magnetic field, which is magnetic field of the loop itself. So this is the book. Next one is about a solenoid. Question saying that a solenoid with the ends marked A and B is suspended by a thread so that the core can rotate in horizontal plane. So a current is maintained in the coil so that electrons move counterclockwise when weaved from end A to the B. How will the coil align itself in Earth's magnetic field? So remember, solenoid is a device which can be used just like a compass because it has N and S. So I'm going to write, and a current is maintained in the coil, move counterclockwise. So they are moving like this, counterclockwise. If electrons are moving counterclockwise, so electric current must be clockwise in the opposite direction of the electron motion. So then if I use right hand rule, so forefinger is pointing the electric current direction, which is clockwise, thumb must point where the end pole is. So end pole of this solenoid is going to be B and B. So this is going to be north. Is going to be this. B and B is the north pole. So and B is the north pole. And when we suspend this solenoid, it's going to rotate in Earth's magnetic field so that end pole must point the north of the Earth's north magnetic field. S pole must show the south of the Earth. So that's why A points to the north. No, A is not pointing to the north. A is pointing to the south. This is not correct. The end marked A points to the south. Yes, as you see, A is pointing to south.